So we're talking about springs. In particular, we're going to look at the force that's associated with a stretched or compressed spring. The force in a spring. I'm not sure if "in" is a good word to use there. The force associated with a spring. And of course, the energy that can be stored in a spring. So we'll start with the force, and we'll look at that. If we talk about the force that's associated with a spring, well, obviously what you have to do is you have to take a spring. Let's say we take this spring like this, and we grab the end and we stretch it out, and we pull the spring, say, to here. What we've done is we have stretched the string from this position to this position, a certain distance or displacement. In fact, if I put an arrow on there to show the direction in which we have displaced the edge of the spring, it goes to the right. And we're going to call that displacement x. We could use a d, I suppose, but a displacement d usually stands for any displacement whatsoever. And this is a very particular one that specifically relates to the amount of compression or stretch in the spring. So x stands for how much the spring has been stretched, or this also works for compression if you want to compress the spring. We'll just do an example of stretched first. Of course, in order to do this, what you have to do is you have to use a force. You have to apply a force to the end of the spring in order for it to be stretched. And when you do that, the spring, according to Newton's third law, for every action force, there's an equal and opposite reaction. The spring force wants to pull back against you with the very same force. So Fs. Now Fs is what I call the force of the spring. But it's important to realize that what it is it's often referred to as the restoring force. It's the force that tries to put the spring back to the way it was. So we often call it the restoring force for the spring. Now I want you to look very closely at the arrows. You'll see that the red arrow and the green arrow, the restoring force of the spring and the displacement that it has been moved through, are pointing in different directions. And we'll get to that in a second, why that's important. So, if we look at the factors that what affects this force on the spring? Well, one thing is the springiness of the spring. How springy is it? So the springiness is sort of an example of whether the spring is a very loose spring that can be easily stretched or compressed, or a tighter spring that takes a lot of force to be able to stretch it or compress it. So the springiness of the spring is another factor. And the springiness is basically referred to as the spring constant. It's a measure of how springy the spring is. And the spring constant has units. The unit for the spring constant is newtons per meter. So what it's telling you is, as you pull out the spring, stretch the spring, it's telling you that the force, the newtons, what that force is going to be for every meter that you pull. Now here's the interesting thing about the force on a spring. It's an increasing force. Force increases as you stretch. So in other words, it's not a constant kind of force. So if you take a spring that looks like this, and you were to stretch it, say, we'll say 1 meter. Normally you wouldn't stretch a spring 1 meter. That's an awfully big stretch. But let's just say, for the sake of getting the units right, we stretched it 1 meter. And let's say you measured the force that the spring was pulling back with, and the force that the spring was pulling back with at this point was 20 newtons. Well, that would indicate that because you've moved a distance of 1 meter, and I'll put the arrow in again, you've stretched this way. Because you've moved a distance of 1 meter, and the force is 20 newtons, that would imply that the spring constant, and the spring constant, by the way, is usually, I'll put it back up here, it's usually a K, a small K for the spring constant. So the spring constant K in this case would be 20 newtons per meter, because a pulling out of 1 meter gave you 20 newtons. Now guess what would happen if you stretch that spring yet again a further meter? Now you are 2 meters away from your original position. Well, guess what? At this point, the force would be 40 newtons, because the spring constant is 20 newtons for every meter of stretch. And so the force is continuously increasing. And that's an interesting thing, because a lot of the examples that we've dealt with in this course have dealt with uniform forces that are constant, not forces that are continuously increasing. So it makes this a unique situation. All right, so we've seen that the force of a spring depends on how far you pull it and how springy the spring is. And so we can say that by writing down F, the restoring force of the spring, is equal to the spring constant K, how springy it is, multiplied by how far you pull it. And because, if you look at that picture again, because of the fact that the direction of the displacement, let me see if I can highlight this in yellow, the direction of the displacement is to the right, the direction of the restoring force on the spring is to the left, then this number should end up being negative. The force needs to be in the opposite direction as the displacement, and so you'll often see a negative kx as the formula to calculate the force in a spring. Now, some books that I've seen just write it like this, and they don't worry about the direction, because what they're actually talking about here, what they're not writing is the fact that they're considering the magnitude only. And you recall that magnitude can be symbolized in mathematics by using absolute value signs, because magnitude means we're not concerned about the direction, or the plus or the minus. When you calculate this way, you are figuring out how much the force is, and you're going to infer the direction. You're going to infer the direction, because you know that it will always be opposite to x. So sometimes we like to do it that way. It depends, I guess, on what kind of person you are and how you like to think of it. The textbook we're using uses this, but I have seen many that use this. So depending on how you want to do it. It is pretty obvious, isn't it, about the direction? If you stretch a spring to the right, it'll pull back to the left. If you compress a spring inwards to the left, it'll pull back, or push back, I guess, to the right. So that's not a big problem. All right, so here's an example. Let's do a little example of how you might use this little question. A spring has K equal to 40 newtons per meter. Okay? How much force is required to stretch it 0.4 meters, which is quite a bit. Well, again, we have to look at, what does this mean? How much force is required to stretch it? That sounds like you're asking about the applied force, not the restoring force. So you go back to our picture. In our picture, we had an applied force. I believe it was in purple. Here it is. And we had a restoring force in red. Well, they are the same force. They're just an opposite direction. So again, this might be a situation where we can appreciate why this particular version sometimes makes more sense when we're going to use Newton's law. But let's figure out F in the spring. Let's just see what happens. If we put the negative sign in, then we have to be extra careful about what our answer means. So if we did it this way, it would be very simple. The K value was 40, negative 40, and 0.4. So 4 times 4 is 16, so that would be about 16 negative. What this tells us is the restoring force of the spring is 16 newtons. So therefore, the applied force that you would pull with would be the opposite of that, or 16 newtons, right? But what a lot of sort of people might do is say the force of the spring is kx, knowing how much it is, 40 times 0.4, 16 newtons. And now you can call that the restoring force of the spring, or you can call it the force that you would pull on the spring with, but we know that the amount is 16 newtons, and the direction we can infer from the context of the question. So either way, it can be used both ways. All right, so that's how you do force in a spring. Let's talk about energy in a spring. Perhaps. No, let me talk about energy in a spring. I was going to try to do something else, but I won't just yet. Force and energy. So energy in a spring, well, we know there's energy in a spring because a spring can do work. If you tighten the spring up or compress it, or if you stretch it, then it has the ability to apply force to something. And that means it can cause something to move through a distance or a displacement. So a spring can do work. So what we want to do is try and figure out something about how we can calculate the energy in a spring. Now to do this, we're going to use a graph. So let's take a picture of a spring. Okay, I'll draw a picture. Here's my initial spring. So let's say I stretch it out first this much, I stretch it out a little bit more, and then I stretch it out a little bit more, and we'll just do 3 of these. Each time I'm stretching it, here's a stretch of 1 meter. Then I'm stretching it an additional 1 meter. And then I'm stretching it an additional 1 meter. Now, let's say that the K value for this particular spring is 10 newtons per meter. That means that here, the force is going to be 10 newtons because it's been stretched 1 meter. Here, if we count how far it is from the original position, which I'll put right here, this is 2 meters, so it will be 20 newtons. And if I stretch it a little bit further, Fn, what am I writing N for? The force of the spring is 30 newtons. And you can see what would happen. For every meter, if we continued this on, we would get 40 newtons, and then we would get 50 newtons, and we would get 60 newtons, and so on. For every meter we stretch it. That's what 10 newtons per meter means. Let's draw a graph of that. So if we drew a graph, and on our graph we graphed the force of the spring, the restoring force, or not the restoring force, the force we pull with, the magnitude only, and then we graph the x, the distance that the spring is stretched. Well, if we drew some dots, we would find that our first set of dots, our first ordered pair, is an x of 1 meter and 10 newtons, right here. So let's put an x of 1 meter and 10 newtons. So for my meters, I'll just make some marks. 1, 2, 3, 4, 5, 6, 8, 9, 10 is enough. And then we'll count by tens here. 10, 20, 30, 40, 50, 60, 70, 80. So these are going up by tens, and these are going up by ones. Well, the first dot that I draw is here, 1. The next dot was at 2, and so what ends up happening is, if we draw all these dots, we end up getting a straight line that looks something like that. Okay, well, how can we figure out the energy if we have this type of a graph? Well, remember that energy is equal to work done. Work is a change in energy. A change in energy is equal to work. So, and of course, work is force times distance. Well, we're applying a force. We're applying the force of a spring, or the spring force, and we're pulling the spring through a distance x. So by multiplying F times x, we could figure out what the work is that's done in a spring. And so if you look at this picture, well, let's see. How would we calculate the area of, say, a triangle drawn right here? Let's call this a certain number x, arbitrarily chosen, right? And this up here would be the force that goes with it. The force in newtons happens to be 10, 20, 30, 40, 70 newtons. 1, 2, 3, 4, 5, oops, 6 with a 7. Should have came out to a better number. My graph's a little off, isn't it? Let me just try to fix that. Sorry about that. 10, 20, 30, 40, 50, 60. This line here, at 60, should of course, 1, 2, 3, 4, 5, should have corresponded to here. So it looks like my line is a little bit crooked. My ordered pairs weren't plotted very well. So let's just kind of do it that way. So there's our spot. It's a rough sketch. Let's say we wanted to figure out the area under the curve, the area in here. Well, to do that, it's a triangle shape. And to do the area under this curve, area equals 1/2 base times height. And so the area of this curve would be 1/2 of the base, which is an x, and the height, which is the force, F. Okay, the area represents the work. So the work or energy associated with this spring stretched to a distance x is 1/2 x times the force. But remember, we just finished saying that force equals kx. The magnitude anyway of the force is kx. So I can replace that with this kx, and I get work equals 1/2 of x times kx, or more commonly written as 1/2 kx squared. It looks very much like the formula for kinetic energy, right? Now, this is the work that would be done by a spring if it was, or the work that you would do on a spring if you stretched it that much. But you could also think of this as the energy stored in the spring. So we often see it written as energy instead of work, kx squared, kx squared. And you can call that the energy in the spring. The energy in a spring is 1/2 of kx squared, which is good. Now we know all about how to calculate the energy, so let's do a little example. Let's do an example where we take a scenario like this. This is a spring inside a loaded toy gun. So there's a gun here, all right? And when you pull the trigger of this gun, this spring is sort of being held by, let's say that there's a trigger here and there's a little mechanism that holds the spring in place. And inside here, you have a little purple ball made of plastic. All right? Let's say this ball has a mass of 0.02 kilograms, 20-gram ball. That's probably a bit much for a plastic ball, but that's good enough. And let's say that this little spring inside here has a spring constant of 40 newtons per meter. And let's say that when you loaded the ball into the gun, you compress the spring. So the spring is kind of compressed in there and being held in place by this device attached to the trigger. And so the x value is going to be 0.05. about 5 centimeters. So that would be 0.05 meters. So here it is. Let's see if we can figure out how fast will the ball be moving when the spring is released. Because when you release the spring, it's going to push back out against the ball and fire the ball out of the gun, preferably not at your younger brother or sister. How fast will the ball be moving when the spring is released? Well, we can use energy for this type of question. We're going to make a couple of assumptions. We're going to assume that it's an ideal spring. An ideal spring is something that doesn't really exist. This means there will be no energy losses in the compression or stretching of the string. Technically, that's not true. In real life, when you stretch and compress a spring, especially if you do it repeatedly over time, you'll noticeably see some heat building up in the spring. And there are energy losses in real life. But for the case of what we're doing, we're going to assume that there is no energy loss. And so if we look at this as a mechanical system, right? A mechanical system is when you look at the big picture and all the types of energy that are involved. The total energy of this system at any given point, say position or point 1, is always going to be the same. You cannot change the total energy of the system. All you can do is change the forms of the energy within that system. So that would mean that at the beginning, right, we have the total energy, which is a spring that is condensed and waiting to move. Nothing is moving. So we can describe that total energy as the energy in the tight compressed spring. There's no kinetic energy, nothing's moving. And we're not going to be concerned about gravitational potential energy because we're talking about moving horizontally, shooting out of a gun. So there's not going to be much change. If this is your gun and you fire the bullet, it will eventually begin to fall to the ground. But we want to know the speed right as it comes out of the gun, right after the spring is let loose. And so there'll be no appreciative change in the gravitational energy either. Now afterwards, at the second point that we want, here, the spring has released all of its energy. So the energy in the spring will drop to 0. And the only thing left will be kinetic energy, where the ball is now moving at a decent speed. And so we can set up our equation this way, and then we realize that the energy in the spring, 1/2 kx squared, will become the kinetic energy after. So you see how we use this little equation as just another form that energy can take. And we do our 1/2, I think I said 40. For the spring constant, I did. So 1/2 of 40, and we said it was going to be compressed 5 centimeters. And so I have to square that, equals 1/2. And now I have the mass, which I believe was 0.02. I'm going to check that as well. 20 grams, I thought we said. Yep, 20 kilograms, sorry. 0.02 kilograms, which is 20 grams, right? And then v squared is going to be the speed. I should be able to solve this without a problem. First of all, I can multiply the whole thing by 2, both sides, and eliminate the half. So I would get 40. And why don't I just do the math here all really quickly, and then if you're not sure, you can. So this side would be 0.1 when it comes out. And this other side is just going to be 0.02 v squared. And I'm going to double check the math just to make sure. So yeah, looks like good. And so if we divide 0.1 by 0.02, we get about 5-ish, I think. So 5 meters per second is, oh wait, no, hold on. Let's not get carried away. 5 equals v squared, so now we have to take the root of that, and that root is about 2.2 meters per second. Fast enough to be fun, but not fast enough to take your eye out, we would hope, with this child's toy. But the main idea here was to see how energy in a spring can be used in an energy equation, just like we used MGH or we used EK. Let me give you another example, and then we'll call it a day. let's take this situation. Let's draw a line here and move on down a little further. Let's say you have a spring sitting on the ground this way. So before you have a spring, all right? And let's say that you've dropped a big rock on the spring, a big rock. And this rock is going to have a mass that we don't know about, m. Now when you drop this rock on the spring, it causes the spring to compress. The weight of the rock pushes down. So we're going to pretend that initially the spring was here and it compressed this much. So this is our x value, and we're going to say that that's equal to 0.08 meters, about 8 centimeters. Right, so originally the spring was here, you put on the rock and whoop, then you bounce a little bit, but then after a while it would just be balancing there. So it's just sitting there. Nothing's moving, everybody's happy. The spring constant, K, is going to be, we'll just make it up and we'll say it's 5 newtons per meter. Doesn't really matter. Some spring constants are very big. If you want a large mass, it could be big. I just keep it at 5, so the numbers are easy to do in the examples, but you could have 450 as a spring constant. You could have 4,590 newtons per meter. Because it is newtons per meter, that's a lot of stretch, so it usually is a fairly large number for most springs. Okay, what do we want to do? What do we want to figure out? Well, obviously we want to figure out what the mass is. What is the mass of that rock? A rock right there. Well, in this case, we would look at the total energy, right? The total energy of the system. So what's happened is there's been a change in the energy of the rock, and there's been a change in the energy of the spring. Originally, we had a spring with no energy. So let's start with our statement of the conservation of energy. The total energy at any one particular place in the system is going to be the same all throughout the system, so it's also the same at any other spot. So let's look at the spot just before the rock was let go, when it was just touching the top of the spring. Let's have a look at that spot. All right, so we'll put this here. What we had a rock that moved through a displacement of 0.08, right? It went from one height and it dropped. So we could think about the total energy of the rock being mgh, Eg, right? There was some Eg. Then there was there any spring energy? Well, we'll put it in here. And was there any kinetic energy? Well, there would have been no kinetic energy when I was holding the rock. Then while the rock moved into position, from position 1 to 2, there would have been some kinetic energy, but afterwards at position 2, I've let go, the rock is now sitting still, so there's kinetic energy in between, but not really at either of the two positions. So let's put this 1 and 1, and the Eg2, and plus E spring 1. Right? Well, what we get here is mgh1, height 1, and 1/2 kx squared, 1, equals mgh2 plus 1/2 kx squared, x2 squared. All right. Initially, we had the mass and the g times h. Now, there's a couple of ways you can do this. We can plug the numbers in right away. Well, yeah, let's do it. That way it'll be simple for you. So the mass we don't know. So it's 9.8 m times h1. Now, there's no kinetic or no spring energy at first because I haven't let the rock go. But afterwards, we have 9.8 m times height 2, and we have some spring energy, 1/2 kx squared. Well, k we said was 5, and x is 0.08. Okay, so we can put 5 for the k and 0.08 squared, don't forget to square it, for the x. Now let's group our like terms. 9.8 mass of H1, and then we bring this over, 9.8 times the mass of H2, right? And that equals all of this little number. Well, 0.08, you can square that in your head. If you square 0.08, you get 0.0064. And then if you multiply that by 5 and divide by 2, I think you get 0.016. Let me just check to be safe. Since we're doing an example, we don't want to screw it up. Times 5 equals divided by 2. Yeah, that looks good. Now look over here. We can factor out 9.8m, and we get H1 minus H2. 0.016. Well, what does H1 minus H2 mean? It means the difference, right? This means the difference in height. So if you subtract two things, that's the difference. Well, what is the difference in height? Well, we know the difference in height is how far the rock fell. X equals 0.08. It's actually seen as the x, isn't it? And so this becomes 9.8m times 0.08 equals 0.016. So actually we could have multiplied that out of one side of the equation, but it doesn't matter. 9.8 times 0.08 equals, so we get 0.784m equals 0.016. And so we do some dividing. It's going to be a small number divided by about 0.784-ish, and we get a mass of 0.02 kilograms, so 20 grams, a small mass. But you can see how the mass emerged from the math. And of course, we could have used this same mathematical model to determine all kinds of things. We could have determined the K. If we didn't know the K, but we knew the math, then you can see right here, this number would still be K, but this M would be a number, and we would work it out and get the K. All of the things that could be asked for exist in this expression. And so this expression will solve any problem that looks like a spring sitting with a mass sitting on top of it. Okay? This is where you always start, because this is the key to conservation of energy. Then you have to make a decision. You've got to think a little bit, use your brain to figure out what types of energy you might have before and what types of energy you have after. And then from there it's easy. It's just basically math. You find the expressions and you work through the rest of the problem until you come up with an answer with what you're looking for. So the trickiest part of this is this first part, where you have to figure out what kinds of energy you have. And now you may face situations where you have kinetic energy, but you also have learned how to deal with gravitational potential energy, and now we can throw into the mix spring energy, 1/2 kx squared. And I think that's as far as we'll go. We'll see you next time.